Hello everyone, this is lecture 24 for the solid state physics, in which we were studying the Drude model. We have completed that, and I have given you some questions for the homework. Hope you tried at home, otherwise here is the solutions. Okay, for the first question we need to find first the concentration N. Then all the terms can be calculated using the formulas. You already have these formulas. Here you have. So first we need to find the concentration. So for sodium, you know that it has BCC structure and it has +1 valency. So electronic concentration, how you will find? It is number of atoms in a unit cell divided by volume in the volume of unit cell, that is atomic concentration, and each atom is contributing 1 electron, so multiply with 1, you will have the electronic concentration. Okay, and in the denominator you have A, that is our length of the unit cell. Okay, so and given is radius is given 1.86 angstrom. So how you can relate them? You know, in the BCC structure it's diagonal, means whole atom is at diagonal, so 4r will be equal to root 3a. okay, you know how to find this. And now you can relate a with r, and r is given, so you can find a and put the value here, and you can solve it and you will find the concentration N. Then you know the formula for the Fermi energy at the 0 Kelvin, that is h cut square 2m 3 pi square n. So this is mass of 1 electron, this is concentration, you already calculated this, put it here, you will find the EF naught. And average energy will be 3 by 5 EF naught, and energy density will be 3 by 5 n EF naught. You have n, you have EF naught, you can put it here. And Fermi radius will be this, and Fermi momentum can be this, and from here you can find, when you already find this, you can find the Fermi velocity from here, and Fermi temperature can be calculated. Now there were B part for the question. What was that? We need to find the CE at different temperatures. So we already proved these expressions for the CE, Fermi energy at different temperatures. That was this. So you have EF naught, and you the temperature is given, so you can find the EF at any temperature. But we basically need to find the CE. So CE at any temperature can be calculated using this formula. You have EF naught, you have given the temperature, put it here and put the R value kV. You can find the CE at the 100 Kelvin and the 200 Kelvin. So you can solve this. Here is the solution. You can find the CE using this formula. It came here from this, and you can also find Fermi energy at any temperature using this formula. Okay, we already know this. Now the next question is repeat for the copper. So we know that copper has the structure FCC. For FCC you have the 3 on the edges, 3 on the sides, side faces, so and 1 on the corners, so 4 atoms total, and divided by volume of 1 unit cell, and each atom of copper contributes 2 electrons because of +2 valency. So concentration can be calculated using this, and A is given here. So we have the N, then we can find all these terms using the formulas for the copper also. Okay, so we have solved these two questions. Now for the third one, we have to find for non-relativistic free electrons in 1D and 2D all these terms. Okay, so let me show you something. Here when we calculated these all the terms, Fermi energy and all, we use this for the 3D. For non-relativistic electrons we use this expression, and this expression came from the density of states. We already discussed the whole part. So if you need to find for the 2D, then just put the expression for the 2D here and do the same. Okay, everything is same, just use 2D expression, then for 1D expression do the same, and you will get the expression for all these values. Okay, try it. If you have still having any doubts, then put it in the comment. I will solve for the particular. Okay, now you need to find all these terms for the relativistic electron, and in all the 1D 2D 3D at T equal to 0 Kelvin. So for the relativistic electron, what you will use? You will use this dispersion relation. E equal to h cut kc. Means for non-relativistic you use this equation, and from there when you have the expression gk dk, then k and e can be related using this formula for non-relativistic, and k and e can be related for the relativistic by using this formula. Okay, that's how you can find the density of states, okay, and the number of states. So use these formulas, and for 1d 2d 3d, and calculate the all the values. Okay, hope you can find them. It's just easy. Oh, sorry. So where will be on the next question? So we need to prove that Fermi pressure for non-relativistic electron in 3D is this. Okay, so we need to prove that pressure is this. So for pressure we know the formula, that is partial differentiation of energy with respect to volume. Because from thermodynamics you can remember that P del V is nothing but energy or work done. So that's how you can see this expression. So how you can find the P? So you need to find the total energy, then you have to differentiate with respect to volume. So we know that average energy is 3 by 5 EF naught. We already proved this. So for n electrons, just multiply with n. So it will be 3 by 5 n EF naught. Okay. Now you have total energy. You need to differentiate it with respect to volume. For that you have to take the V expression also. So 3 by 5 n, and EF naught we know this, h cut square by 2m 3 pi square. It is small n, that is n by V 2 by 3. Now differentiate it with respect to volume. So it will be 1 upon V 2 by 3. It will be V minus 2 by 3, and differentiate, you know how to do that, minus 2 by 3 and then minus 1. Just it's a simple differentiation. When you solve this, then 1 upon V will came in, and there is one more V here. Okay, and this n by V will turn out to be small n, and this is again the expression for EF naught, and we will cancel this, and 2 by 5 you will get this expression. Just try to solve this, just normal differentiation. Okay, you will get this. Now the B part, prove that the bulk modulus is 2 by 3 n EF naught, and bulk modulus is nothing but stress upon strain, that is delta P pressure, delta V upon V. It will give you this. Now you need to find this. So you have already the expression for P, that is this. Put again the EF naught value, that is this, and when you solve this and differentiate with respect to volume, you will get here 5 by 3 some expression. 5 will cancel out, and you will get 2 by 3 and the required expression and EF naught. Okay, these are just easy, just a simple differentiation. Okay, so I hope you haven't, now you have not any doubts. Okay, if you're still having any doubts, then put it in the comment section. I will try to resolve them. Okay, let's move to the next topic. Well, it's not next topic, it is related to what we were discussing, that is the resistivity, conductivity we were talking. So now we will see the temperature dependence of resistivity. Okay, and the Matheson's rule. So what does it say? So we know that inside a conductor there is a resistivity. Okay, we already know that. So where it came from, and what is the origin of that resistivity? So there are many factors, but the main thing is this is total resistivity is sum of rho naught plus rho pH. This resistivity came from all the defects inside the conductor, defects and impurities we have, and this resistivity came through the phonons. Okay, the vibrations. Phonons are nothing but vibrations, and that wave energy carries the energy, and that quanta of energy we call that phonon. Okay, so what is rho naught here? Resistivity due to scattering of electron from impurities. Okay, the rho naught is nothing but the hindrance to the electrons from the impurities inside a conductor. Okay, so that gives you the resistance and the resistivity ultimately. And rho pH is nothing but resistivity due to scattering of electron from the phonons. Okay, and we have this relation 1 upon tau equal to 1 upon tau naught plus 1 upon tau phonon. This is tau is nothing but relaxation time or mean free time. Okay, So how you get this expression? So we have these expression already proved these. The drift velocity is nothing but minus e tau e by m. This is current density, n is square tau by m e. Okay, this is sigma e actually, and sigma is nothing but this one, n is square tau by m. And from here we can calculate the resistivity, that is reciprocal of conductivity, m over n is square tau. And we also know the mobility. And mobility, how you define that? That is drift velocity per unit electric field. That is mobility. It is equal to e tau by m. Just from here we came this expression. And sigma can be written as ne mu. Okay. So you have this expression. The m, n, and e. These all are constant. For rho, for the impurities, it will be tau naught. For phonon, it will be tau ph. And for overall we will write rho total. And so from here we can get this expression. Okay, means 1 upon tau will be 1 upon tau naught plus 1 upon tau ph. Then just this will common out and cancel out, and you will get this expression. So this is Matheson's rule. Okay, so now let's see the temperature dependence. First, the rho naught, that is impurity 1. So it is independent of temperature, because you know that inside a metal or a crystal, the structure will always remain same. Means structure and the defects and impurities it have will always remain same. It won't vary with the temperature. That's why we have the constant rho naught with temperature. It will remain same. Okay, but the phononic resistivity will vary with temperature, and it will vary when the temperature is low. Then it will vary proportionally with the T to the power 5, and when the temperature increased, then it will be linear with temperature. Okay, so if I become the I be the specific, then specifically that is divide temperature. If temperature is very less than divide temperature, then it will be proportional to T to the power 5. But if temperature is greater than divide temperature, then it will be proportional to T to the power 1. Okay, so you can see here that in starting it is T to the power 5. It is parabolic, some not exactly parabolic, but it is some curve. Then it is a straight line. Okay, so just remember these curves. These are very important for the exam. If we combine these both of the graphs, then we will get this. With temperature, the resistivity vary like this. Initially it will start with rho naught, then it will go like this. Okay, and this is nothing but rho naught. So I hope this is clear to you. Now let's see the thermal conductivity inside a metal or the conductor, metallic conductor. Now you know that how a conductor can conduct the heat. How it can? So basically we have two things which can conduct the carrier. These are the electrons inside the conductor and the phonons. Only these two carry the heat. Okay, so we have two carriers, that is electron and phonon. These carry the heat from one point to another. And heat will flow only when there is a temperature difference, and here is a high temperature, here is a low temperature. Heat will always flow from high temperature to low temperature. Okay, and there are some terms like K. We call it the coefficient of thermal conductivity. We will see what is this. Okay, now just see that if here is T2 temperature and it is T1 temperature, and T2 is greater than T1, then heat will flow like this. Okay, and this x is length, then dx, the dt by dx means the temperature difference with respect to this is always negative. Means if you calculate from here to here, this will be less difference as compared to from here to here. Okay, and this one is greater than this one. Okay, this one is तरह से. Okay, so it will always be negative, means the gradient of temperature difference. I hope it is clear. Now let's see what is heat flux. We denote heat flux by JQ. It is nothing but amount of thermal energy per unit area per unit time, and that is cross section. Means the thermal energy passing through a unit area per second, that is called the heat flux. Okay, and heat flux is directly proportional to the temperature gradient. Means the more the temperature difference, more the heat flux. Okay, means here is the more heat flux as compared to here, ठीक है, means because here is we have a large temperature gradient, that is Tt dt by dx, and it is decreasing, means it is negative. So jq is nothing but minus k dt by dx. So just remember this formula. This is heat flux, and it is related to thermal conductivity, coefficient of thermal conductivity, like this. It is dt by dx, and dt by dx is always negative. Okay, I already told you how, why, and that's how jq will always remain positive, because minus minus plus. I hope this is clear to you, what is k, what is jq. Now inside a metal, the main carrier is electrons. Okay, because of a very large concentration of electrons inside a metal, only the electrons conduct the heat. But in an insulator, heat is entirely carried by the phonons, because electrons are not free to move. Okay, that's why in an insulator heat is entirely carried by phonons. In metal, heat is carried by electrons and phonons both, but the concentration of electrons is 100 times inside a metal than phonons. That's why only the bigger factor here is electrons. Okay, in most metals, the contribution of electrons greatly exceeds that of phonon. K is greater than phonon, so large concentration of electron. That's why K is also sum of both the coefficient of thermal conductivity due to electrons and due to phonons, and K is proportional to Ke in the metals. Okay, and in gases we can write the formula for K, that is 1 by 3 Cv V and lambda. Just remember this formula, we don't need to prove this. Here Cv is specific heat at constant volume for the gases, V is the average velocity, N is the concentration, and lambda is the mean free path. Okay, in gases we have this formula for the K. In metals, this Cv will turn out to be Ce, and V will turn out to be Fermi velocity, and lambda will turn out to be lambda f, that is mean free path at the Fermi level. N is the concentration of electrons. Okay, so just remember these formulas, very important. Now we know, we already proved for in the metal what is the formula for Ce, that is pi square by 2 kb square T by Ef. Okay, this is the formula. You can see in the previous lecture, you can find this formula easily and write it as it is Vf and lambda f. Okay, now we know that tau f is nothing but this is time, and time is distance upon speed, so lambda f by Vf. So you can substitute lambda f here with tau f Vf, so it will be Vf square and tau f, and here the Fermi energy can be written as half m Vf square. Okay, so Vf will cancel out and you will get this expression for the K. Now what is the point here? Okay, what we trying to see? Actually we are not trying to see, we are actually seeing this expression. And you can see that thermal conductivity have this tau f in the expression. And what is this tau f? This is nothing but the relaxation time we have find in the electrons or for the metals in the electrical conductivity. Okay, so electrical conductivity is related to the thermal conductivity. From here we can see this expression that they both are related. Okay, remember this, we already proved this expression that conductivity is expression is N square tau f by m, and C means if sigma is related with tau f and K is also related with tau f, means this sigma, this is electrical conductivity and this is thermal conductivity, coefficient thermal conductivity, they both are related to each other. So substitute the value of tau f from here and here, so you can get the relation between K and sigma. So relation you will get is this: K by sigma will be equal to pi square 3 kb square by E square T. Now we call this Widman-Fresnel law, this the ratio of thermal conductivity and the electrical conductivity. Okay, and it is temperature dependent, and if you take this temperature this side and it will get K by sigma T, then this expression become constant. because these are all constant values. This kb, Boltzmann constant, and the electron charge, these all are constant. So we call this a Lorentz number. Okay, the value of this is called the Lorentz number, and this is constant, universal constant. And this is the expression 2.45 into 10 to the minus 8. This is Lorentz number, watt, ohm, Kelvin minus 2. Okay, so this was a big achievement actually, because here we related the electrical conductivity and the thermal conductivity, and Lorentz calculated this thing. So that's why we say this Lorentz number. Okay, so just remember them. Now there is some more things you need to know. Now conductivity at the height frequency means how the conductivity related with the frequency. Okay, in the DC current and the AC current. So I think that you have this idea about that DC current flows through entire body, means in the entire body electrons flow. If you have the potential, then electron will flow inside the body and you will have the current. But in the AC current, the current only flows at the surface. Okay, means electrons only at the surface, only the surface electrons contribute to the current, but here all the body electrons conduct. Okay, so in the AC current, if we see that we have skin depth, the distance from the surface into body up to which AC current can penetrate. Okay, so there will be some length up to which the current will flow at the surface. That depth is called the skin depth, and we have the formula for skin depth, that is rho, this is density, pi f mu, this is frequency, this is permeability. Okay, so this is the expression for skin depth, and from here we can see that if frequency increases, skin depth decreases. And just think, if skin depth is very small, then only few electrons contribute to the current because of the surface, and if skin depth is large, then there will be large number of electrons will be contributing to the current. So it is directly related to the current inside a conductor. So if we have the frequency very large, like 1 megahertz, then skin depth will turn out to be it is 0.06 meter something. This is 0.06 mm. Okay, but for the 50 hertz frequency is very small, and you will have the skin depth 30 mm. Means if this is wire, then up to for the 50 hertz up to 30 mm the electrons can contribute for the current, means there will be large current. But for the 1 megahertz frequency, this width will be very small, and then the number of electrons will be small also, and the current will be less as compared to this. Hope you get this idea that how frequency is related to the skin depth and the current. Okay, so now let's see the conductivity relation of this skin depth and all for the AC current and the frequency. Now this is also for the AC. This is also for the AC. So if we find the current density, then this is conductivity for the DC. Okay, and if we write this is the expression for the AC, and this is only for the DC. Okay, so that's how they related to each other. Okay, means from here you can see that if frequency is increasing, then current is decreasing, means definitely conductivity is decreasing. So this is the relation how conductivity decreases from the DC, okay, in the AC. So this is the relation, you don't need the proof, just see this as it is. 1 upon 1 plus tau square omega square cos omega t, and this is the way. Now we know that what is sigma DC, that is n square tau by m. Okay, this is the expression for the conductivity in the DC current. Now let's see, if omega tau is very less than 1, then how this expression will turn out. Okay, and this expression is for the this circuit where electric field is E naught cos omega t, then current density will be like this. Okay, so omega tau is very less than 1, then this will turn out to be 1, and this will be 0, and you will get this expression Jx will be sigma dc E naught cos omega t. Means this is same as for the DC, same almost, means conductivity will remain same as the DC. for the omega tau less than 1. But what happens when this reaches 1 or greater than 1? Okay, for less than 1, metal behaves as a pure resistance with sigma equal to sigma dc, means it will remain same for the AC and DC both for the small value of omega tau, means less than 1. Okay, so we have some graph with the frequency relation. Let's see. Means initially when omega tau is less than 1, then sigma omega for the AC current will remain same as sigma DC. But when it reaches omega tau is approximately 1, then what will happen? Tau, the value of tau is approximately 10 to the minus 14 second. Then omega should be 10 to the 14 for to make it 1. Okay, so that high frequency means omega is 10 to the 14 hertz. So what happens at this frequency? At this frequency we will see that omega will start decreasing, falling. Okay, and it will decreasing very fastly, means conductivity will decrease. Okay, and this is the actual relation for the AC current. At high frequency it will give less current as compared to DC. Okay, at high frequency. So just remember this curve. Okay, so at what point it will start decreasing, means very sharply, that is when omega tau is equal to approximately 1. So let's see what is this frequency. Omega 10 to the 14 hertz, omega is 2 pi nu. So from here we can calculate mu. It will give you this 10 to the 13 hertz, and this lie in the infrared region, means it is very high frequency. So normally the circuits we have in our homes or the applications we have, they don't have this high frequency for the AC current or the AC voltage. So we don't need to worry about this, because we normally use this 10 to the 6 hertz, megahertz, and somehow this frequency and this frequency. And for these frequencies we have the conductivity remains same for the DC AC both. It doesn't vary, means it will only vary when the frequency is very large, means up to this range 10 to the 14 hertz. Then conductivity will decrease and the current will not be conducted inside a conductor. Okay, so this is the very important information you should know. Okay, there are some multiple questions and can be asked directly. Theoretically you should have this idea that how conductivity vary with frequency. Okay, from the DC conductivity. In the DC it will remain same, it won't vary for anything. Okay, so I hope you get the idea. I tried my best to explain this. If you're still having any doubt, then you can put it in the comment section. I will try to resolve your issue. Okay, thank you. In next lecture we will start the Hall effect. Okay everyone, bye bye.